Section 2.1 is an introductory section to sets, and as such, it has mostly vocabulary, so you could read this vocabulary in the book, in the software, in the videos, you could see it, but I thought I would just emphasize some of what I think the most important is. So a set is a group of things, and in this case, we're going to have a set built out of these three numbers, 0, 1, and 2. Order doesn't matter, so if I say the set that has 0, 1, and 2 in it, it's exactly the same as the set that has 1, 0, 2 in it. Order doesn't matter in a collection called a set. The first way to describe a set is the description. This is one way to describe this set. Can you think of another descriptive phrase that describes the set? You could just say the set is the numbers 0, 1, 2 in words, and that would be a description. There's all kinds of ways of describing those three correctly, and each one of them is a valid description of the set. Roster form is kind of like just writing all the elements down, but we use this little brace, kind of curly brace bracket thing to delineate that it's a set. So the set of numbers 0, 1, and 2. This would be roster form. You use the set bracket notation and you simply write down all the elements of the set. Again, order doesn't matter, so could you do this in roster form in a different way? Sure. You could write down the set that contains 1, 0, 2, and it's the same set. They're equal sets. Set builder notation is the fanciest, and it is useful sometimes. It's extremely compact and useful, and other times it seems useless. The way this is read is kind of official. It is the set of all x's such that, and then there's a description. The set of all x's such that 0 is less than or equal to x, and x is less than or equal to 2. That describes this set of numbers pretty well, but it is wrong. Can you think of why it's wrong? Here's a clue. What about the number 1.5? Is it in this set? And the answer is yeah. The set of all numbers x such that this is true. Well, 1.5 is in between 0 and 2, and 1.5 we don't want to be part of the set. So we need to fix up this set notation. Set builder notation can be tricky. It's very useful, but it can be tricky. So how about this? X is the set of all x's such that 0 is less than or equal to x, which is less than or equal to 2, and x is part of the set of natural numbers. That works pretty well. Let's take a look at what that means. This is a member of, an element of, one of the numbers in the natural numbers. The natural numbers are counting numbers, 1, 2, 3, 4, 5, 6. So that seems to work pretty well. Can you think of a problem with this? Well, what about the number 0? We want 0 to be in our set, but is 0 a natural number? No, it's not. And so let's fix this up a little further. Let's say x is a member of the whole numbers. The whole numbers are 0, 1, 2, 3, etc. Now this seems to work. We're saying that x has to be one of these kind of numbers, and it has to be in between 0 and 2, including 0 and 2. So set builder notation is a bit tricky, and I wanted to emphasize it a little bit extra. We're only going to work with sets that are well defined. We're not going to work with sets that are not well defined. Like, what would be an example of a 3-element set that's not well defined? Well, what if we had this set of the 3 most liked people in the world? Well, it's just very non-specific. It's anybody's guess who was being talked about. I mean, it's completely and totally non-specific, and that's not well defined. So we're going to deal with things where it's pretty clear what elements are in the set. An empty set has no elements at all. It doesn't have a zero in it. It has absolutely nothing in it. It's empty. And one way to write this, it's kind of laborious, is to just put the set brackets with nothing in there. Again, not a zero, just with no elements at all. Another way to write it is with an O with a mark through it like that. That means empty set. Infinite sets are sets that have more than any number, so it has more than 7 elements, more than 20, more than 30, more than 1,000,000, more than anything you can imagine. And for the most part, sorry about that, for the most part, we denote an infinite set by putting some sort of pattern and then a ... which means that pattern goes on forever. This is not something that you could number, like, are there 10 things there? No, there's more than 10, because you could list the first 10 and then there'd still be more. So this is an infinite set. Let's do a practice problem. Here we have the set A. Notice set letters that are kind of variables that represent the sets are usually capitalized. So we would like the goal is to write this in set builder notation. So we're going to say the set of all. I usually use X because it's boring and easy, but you could use really any letter you want except perhaps A. So you could have the set of all Y's such that Y, but X is the routine, so let's use it. Set of all X's such that X, I was going to put is a member of, but I think instead I'm going to practice using X is an element. X is one of the numbers in the natural numbers. Remember, the natural numbers are 1, 2, 3, etc. And X is a multiple of 7. And that seems to do the job nicely. This next question is a bit tricky. It's tricked a lot of people. It's made a whole bunch of people uncomfortable, some of whom were mathematicians. Take a look at these two sets, the set A from the previous problem and the set N, which is the natural numbers, the counting numbers, 1, 2, 3, etc. These are both infinite sets. But I'd like you to notice something. I'd like you to notice that these numbers are contained in these numbers. So for instance, this 7 is right here, the 14 would be out here, the 21 would be out here. This looks to have more numbers than this one. In fact, it looks like there's 7 of them here for this one here, and there'd be 7 more for this one. It looks kind of like this might have 7 times as many numbers, and it might be 7 times as big, and that seems sensible, but it turns out, a little bit later in this class when we study infinite sets, it turns out that these have the same number of elements. The number of elements is sometimes referred to as this. The number of elements of the set A would be written this way, and this is an infinite amount. And so these are both going to have the same number of elements, the same infinite amount. These two sets let's call this the set C and this the set D. So the number of elements in the set C is 4, and the number of elements in the set D is also 4. So these are not equal sets. They don't have exactly the same elements. They share some, but they don't have exactly the same elements. So they're not equal sets, but they are equivalent. Any two sets that have the same number of elements, the same cardinality it's called, those two sets, if they have the same number of elements, are called equivalent. The last idea I want to emphasize is the idea of a universal set. There will come problems where we're working with a set of numbers like 1, 2, and 7, and we will want to identify the numbers that we are not working with. So if this circle represents the 3 numbers we're working with, then what are these numbers out here that we're not working with? And we don't want them necessarily to be the rest of the numbers in the universe. And so what we have is kind of the universal set for this problem. And the universal set here might be the numbers from 1 to 10. And that just means in this entire problem we're using 1 through 10, and right now we're working on 1, 2, and 7. So the things that might be out here would be 3, 4, 5, 6, 8, 9, and 10. There's no 12 in this problem. There's no 17 in this problem. So the universal set is kind of all the numbers that can be used in a particular problem. And we won't really use the universal set yet, but it's an idea, a definition, some vocabulary that we're going to use in the future.